to move in one direction, changes the force or the interaction when it changes the zone. Okay. So now I want to. I'm not sure about who is going to stay the entire weekend or not. So we will just define that this morning, I guess, and see how we share the job between these two things, or if we just decide to focus on one for now for the rest of the weekend.
Okay, do you have anything you need specific help with, or?
I think I will have question to Giuliano to keep going on what we started to do.
Mm-hmm.
And maybe I will have a few questions about rates equation for the ODE for cell population dynamics to people that have worked with that. So if anyone has, is ready to talk today, I will be happy.
I think I could probably help with that. Josh is the big expert on how to translate ODE models into spatial models. So maybe Josh could join your group for a bit and then discuss some. So
this is not even at the state of translating. It's just like looking at the different papers, and people are using different types of equations, and having someone that has some background would maybe help us to just find what is the most relevant for us. Yeah, thanks.
Okay.
I don't know if anyone, so Josh was in our group as well, so maybe he wants to discuss more about this project.
Yeah, thanks, Cyril. I had to step out for about half of the afternoon yesterday, so I'm still at the stage of the biological model development, and also because of the timing issues, I wasn't able to work with Jimmy, who also wanted to work on the mucosal immunology project. I think the goals for the morning are just to finalize the elements that are going to be in the model and how they interact with each other. I think I probably got a little too lost in the weeds yesterday trying to find really like firm quantitative data. I think one of the problems with the model system that I've been working in is the sparsity of time points. So it's a little harder to know exactly what the behavior is. But in terms of like how the different parts work with each other and where they are anatomically within the skin layers, we have a sense of that data is known. So I think we can start to move forward early today to start to construct that. Yeah. So I think we can, I mean, in terms of talking with the organizers who were in our forum, Yi and Giuliano, they both, I talked through the likely representations of the problem on CC3D, and then they thought that those would be relatively straightforward. It would be a lot of like diffusion of chemokine fields attracting like immune cells and having them chemotax out of vasculature through different cell layers. And actually seeing Cyril's work on the movement of cells through the thymus was even helpful for me just to have that going in another screen and to watch how they were programming that. So hopefully pick up more today.
Well, I'm happy to join. I'll try to circulate today again and stop in with everyone. And I don't know, Jim Sluka has also got a lot of expertise, so he can probably help out too.
Okay, great.
Yeah, especially for setting up your initial conditions and things like that.
Okay, that would be great.
Great. Okay, the next one on my list is vascular tumor models. You want to give us?
Mehdi, are you there?
Yes, I'm here. Actually, yesterday we started to model I want to share with my screen. These things, but because my knowledge about the procedures we have followed in our lab was narrow, we didn't manage to complete the model. But now I know that we are using endothelial cells to form this vascular network. And we are going at the first step, we are going to see that, how the endothelial cells form this kind of irregular vascular network. This is the first aim we want to follow. And also after that, we want to see that if you put, because this is hydrogel, this is empty space, and these are all endothelial cells. We want to see that if, for example, put a cancer cell in the empty space, how it will be attracted or adhere to the vascular network. This is the two purpose and aims we want to follow and model. But yesterday we went through the package and we tried to make ourselves familiar with the package, but we didn't actually start working on these problems. But I'm hopeful today we can at least to make an initial model for this problem to see that how endothelial cells can form a vascular network on the hydrogel, and how the cancer cell will be adhered to the vascular network.
Let me explain a little bit. So I'm Yang Lu from Lehigh. We have been working on this vascular flow problem for a long time. So basically my lab focused a lot about biofabrication and microfluid device. So recently we were trying to culture those in the cellular cells in different gels, JAMA or Matrigel. The goal here is that we're trying to create a hierarchical vascular network branching from larger arterial scale all the way down to capillary scale. So the image showing over here is capillary scale network, where we culture a network, and it's not even a network. This is actually self-assembled cellular cell. They kind of form and join, form tiny 10 micron vascular tubes. So we were excited to see this because this is pure in the cellular cell without even fibroblast or tumor cell. They just self-assemble in 3D Matrigel into this tube. So that motivated us to think about how do we form those network better or more uniform way, so that we were thinking of either adding a tumor cell or adding fibroblast to stimulate the self-assembly process, or changing, let's say, the cell concentration to see whether they can form like bigger diameter of the vessel, or trying to infuse like the nutrition flow, such as blood flow, to see whether they can actually increase in terms of size, depends on how large the pressure we apply or how large the flux is. So we were very interested in two problems over here. One is that how does this self-assembling process happen? Why do we got, from those spherical shape of in the cellular cells into a tube shape of structure, right? How do they self-assemble together? And second, we're interested to how do we apply external stimuli to guide assembling process, such as applying a pressure to infuse some liquid flow. Would that promote their growth? Or how do we change the cell concentration? And do we got different diameter of vessel if we tune their concentration? Or let's say if we grow a tumor fluid in the middle, will those vasculature grow inward toward the tumor? And will that actually increase or shrink the tumor growth? Or when we add in drugs, how does the vascular dynamic change with the tumor? Because we did a lot of drug tests before as well. When you have vasculature versus no vasculature, the drug response of the tumor is totally different. So we're interested, how does the vascular dynamic interplay with the growth or shrinkage of the tumor over there? So that's why we were interested in this tool you're using, and see whether that will help us to develop some, cool model that can explain what we observe in the experiment and also guide our experiment.
Okay, so I put two links into the chat. There are quite a few models using CompuCell of vasculogenesis using HUVEC cells on Matrigel. And there's even one of the demos that's packaged with CompuCell is a model of HUVEC self-organization in 2D. There are also some 3D simulations that are also in the demos package. And the little vascular tumor model that Gilberto's been working on with people is based around these ideas. Of course, if you're doing in vitro assembly of HUVECs, you generally don't have blood flow. Connecting those engineered capillaries to flow is complicated. Some people could do it. I know Roger Kam says he can do it at MIT, but it's not easy. But you could build a simple model where you say that you imagine the capillaries are connected to blood flow. In that case, they act as a source of oxygen and glucose. And that vascular tumor simulation that Gilberto was working on with people is based on that idea. And you can also include various kinds of vascular remodeling, both proliferative, chemotactic, and others. And you can also have the cancer cells respond chemotactically and in other ways to the vasculature. So I think the kind of modeling that you want to do is pretty feasible, depending on the level of detail. Yi Zhang, who I don't know if she's going to be able to join us today, but she's published some papers using CompuCell to model cell migration from tumors in vitro that could be useful. And so there's actually quite a bit of work that's been done using CompuCell or similar methods for addressing more or less exactly this problem. And we're happy to work with people on trying to refine those ideas. Gilberto, as I say, has a lot of experience with that. He's probably the person in the group that has
I have two questions actually for this modeling this kind of problem. One is that I don't know whether CompuCell can model the cell morphology change, say how does the pure spherical shape of cell they elongate and then form this kind of tube shape. I don't know whether it can handle this kind of cell morphology change. Another one is that let's say if we have a separate blood flow model, can we couple with CompuCell3D, right? Because like fluid flow doesn't necessarily need to be done within CompuCell3D. We can have a separate software for that.
So both of those things, so there are three questions, one of which is, can you do cell elongation? And the answer is you could certainly do elongated cells in CompuCell. And there have been a variety of models of vasculogenesis that do that. One of them is one of the ones I just put into the chat. One of the things that's an issue, which is what that first link was about, is that actually, if you look at the vasculature that you have here in this culture, the shape of those cells is non-physiological. And there's a technical problem that Matrigel gives levels of VEGF and a couple of other growth factors that are non-physiologically high. And so that the endothelial cells respond rather badly to Matrigel culture. And so if you look at angiogenesis and vasculogenesis in a more organotypic environment, some of the morphology, it still forms the vascular network, both in this case and others, but the morphology of the cells is somewhat different. And so that's something to think about when you're doing the simulations. You could certainly reproduce what you see in a Matrigel culture, but that actually may not be what is happening in vivo. The second question was about, so cell elongation is not a problem. Tubulogenesis is outside of the reach of any simulation package at the moment, mainly because we don't understand biologically how endothelial cells reorganize to form vascular tubes. What's going on in terms of cytoskeleton during that tubulogenesis, vacuolation and tubulogenesis is not understood at a scientific level well enough for anybody to have been able to build a model successfully of that. in principle, one could build in CompuCell a compartmental cell model that would allow you to create vacuoles inside of the endothelial cell, and connect them together, and that would be quite interesting. It would be pretty challenging. Andy's modeling methodology would be good for that. But the problem there is that there's so much scientific uncertainty, we really don't know the mechanism by which that happens. And so I think that one is tough. And so typically what these models do is they can treat the endothelial cells as a strut that define a capillary, and you say then that you define it instead of as a solid strut as a tube. And then you use, for example, a Kirchhoff type solver to calculate for a given set of boundary conditions, pressure boundary conditions, what the flows are. And so one could definitely say that CompuCell calculates the architecture, the diameter, and the morphology of the vasculature. And then you pass that morphology to a different package, whether it's a Kirchhoff type solver or a more elaborate model of fluid flow. You pass that morphology to a fluids package, and the fluids package passes back the flow rates and oxygen concentrations at different places, which you then use to supply oxygen and other nutrients to the field. That's more or less how we did it in our work on liver toxicity and in our work on diabetic retinopathy. And so actually coupling CompuCell to a better fluid solver would be a great thing to do. I wish Maciek were on the call today because it's something we've talked about over the years. Depending on how your software is written and what the interfaces are, you could definitely have people like TJ and Josh, not TJ, Giuliano, Maciek talk to you about what's involved in calling a second package. Depends a little bit how those are written and things like that. And so maybe we'll talk, I'll join your group and we can talk about that individually, but it's a very interesting problem. And coupling to fluid solvers is something we've talked about for a long time. Maciek did, for example, a provisional integration with the Phoenix fluids dynamics package. And that it's certainly possible to do that. So I think there's some very good problems to work on there. But
that's
if you
perfect.
want,
Yeah, what you describe is exactly what we're looking for, because fluid dynamics itself is not a problem.
No.
It's coupling with the self-assembling process. So we don't necessarily need to, as you described, figure out how the tube is formed. That's not really our focus, but we are interested in how those self-assembling, like morphology, right? Why those capillaries grow in that direction, what kind of network it forms, and how does this kind of network change with your stimulation of either flow or VGF factor gradient. That's what we're interested, not really tube formation itself.
Right. So people have certainly done simulations, and again, I don't want to take too much time now, but I'll join your group and we can talk in more detail. People have done simulations where you have a refinement rule, where you calculate the flow velocity in the vasculature, and you say that if the flow velocity is above a threshold, the tubes get bigger. If the flow velocity is below a threshold, the tubes get smaller and eventually degrade, which is the refinement process that's believed to occur. So it's a Hebbian mechanism. And you can then have a gradual pruning and refinement of the vascular network that you can implement. People haven't done that so much with CompuCell, but there are plenty of examples in other packages that could be imported pretty directly and would be likely to work pretty well for that. So I think that's those are very practical things to do. They're definitely things that could be done. So I'll join your group, and Gilberto will be there, and we can talk about that in more detail. That's great. I think it's a really good problem. So, okay, Katie, how are bacterial motility issues coming today?
They're going well, thank you. So we've set up, our plans are basically to get a element model in both. Me and Harry are going to work in one in CompuCell, and Andy's going to work simultaneously setting up something in Mechanica so we can compare them. we're going to be looking at the role of the individual cells in the filament and how they each contribute to the motion, and ideally progress to looking at a slime secretion and how that's going to have the filament interact with the surface. So far, we have pretty much laid out our overall plans, and then Hariana has set up yesterday a filament in CompuCell. I don't know if you want to summarize that now, Hariana.
Yeah, sure. Give me a sec. Let me start sharing my screen if I can. Okay, can you guys see my screen?
Oh, that's fine.
Yeah, so we started basically initialized the first cells where we have a leader cell and follower cells of the cyanobacterium. And then we kind of implemented in the XML code focal plasticity plugin so that we could connect each of the cells. And then also implemented an external potential plugin on the leader cell so that in the negative X direction to get it moving. And we played around a little bit with the parameters so that we could, get the cells moving in a single straightforward direction to start off with as a kind of a basic model. And so far, this is what we got. We see a lot of clumping, which is kind of not what we wanted. So we're going to keep playing around with the parameters to see if we can get all the cells going forward in a straight line. And then, yeah, we want to increase the complexity of the model. And a few things we want to do is we want to move the plugins, the focal plasticity and the external potential plugins to Python steppables. So we definitely could use some help with that. And then also kind of took a look at the paper that you mentioned by Andreas Deutsch. Mm-hmm. And he does build a model of cyanobacterial movement. He focuses both on single cellular movement as well as collective, but we're only interested in the single cellular one. But he builds a model that's pretty relevant to what we're doing. So we want to do that. He uses like a compartment cell model. So maybe we could replicate what he has. So we definitely need help with that because I don't think either me or Katie have come across that. So yeah.
Okay. So if you're just a few quick comments, other people may have suggestions too. If you're getting the cells to clump up like that, that suggests that the cell adhesion, you probably want your green cells not to stick to each other very much.
Yep. Oh, okay.
And so if you reduce their adhesivity, then they won't clump. Okay. And I can't tell if the links are breaking or not.
Yeah.
But those are, we specified kind of a large gap between them, but we can change that.
Right, but I think that if you simply make the green cells not want to stick to each other, they will stay in a line instead of clumping up, and then you could change the size of the cells and the link properties to get it to stay in a linear chain.
All right.
And I'm happy to join the group and work with you on that. But actually, you're not very far from having what you need. If you couple the cells and drag them, you've got 70% of what you need. So I think you're actually pretty close.
Great.
And,
that's great.
Again, in the time scale of the workshop, we didn't really have as much time to play with parameters. So if we had a semester, we'd spend a couple of weeks doing nothing but playing with adhesion parameters to understand how things behave in that regard. But I think for this looks quite good, and definitely doing the definition of the links in Python gives you a little bit more control over how the system behaves. But I think you're actually not very far from having a chain of cells that you can use to to drag around and have them move actively.
Okay. Thank you.
Anything else you want to bring up with the group? No?
Not for me. Katie?
Yeah, at this point, I think we're sort of, we could do with maybe a little bit of help with the links. I worked on translating the XML into a Python stackable for the FPP this morning, but that sort of still needs a little bit of work, of course. But yeah, and I guess get to the point of the secretion, we'll probably want a bit of help on that.
Okay, that sounds great. We'll definitely be happy to work with you on that. Lateral line people, lateral line and EMT people, do you have a report?
Sure. I'll share my screen. Yeah, so I had a really fun and educational time working with our team, with Yi helping us and Divyoj and Monica. Our goal was sort of our first modest step was to start with this delta notch model that we had been introduced to during the tutorials, but to modify it in a way such that the adhesivity between the cells becomes a function of whether you are expressing high or low levels of delta or notch. And the idea was that cells with high levels of notch activity had also very high levels of adhesivity to each other, whereas cells that had high levels of delta had low adhesivity to the neighboring notch cells. And the question we were trying to explore was whether introducing this feature where the adhesivity is linked to the level of notch signaling helps to spontaneously reorganize the cells to form rosettes with delta cells at the center surrounded by notch cells. So that's what the goal was. And Yi got us started with it. Divyoj and Monica both independently helped develop the model, which I then helped, I modified in this example I'm going to show you. What I have done is actually created a field here, which is going to become representative of the sort of the lateral line primordium, which I will eventually continue to develop. And I've added a few extra features, which are different from the original model, in that instead of having periodic boundaries, these are actually no flux boundaries, so that it's a sheet of cells which has got edges. And those edges are important because they illustrate a particular problem that we need to address in trying to understand. So I'm going to run this thing. And what you see is initially cells get selected at the edges. This is a problem with lateral inhibition, which actually drew me to the puzzle that I'm trying to solve. But what you can see is as cells, high delta cells get formed in the middle, they do exactly what we were exploring would happen. That is, they become small and they get surrounded by this rosette of notch expressing cells. So in some sense, the model has been, it's doing what we were hoping to explore. So this is very satisfying, but it's also revealed the way we were implementing the model had some shortcomings which we were trying to work around. So the idea that I had originally started out with was whether we can make the adhesivity directly a function of notch. But the way the contact feature works in CompuCell does not allow us to dynamically vary that adhesivity very easily. So for this version of the program, what we had done was simply say that if a cell has greater than a higher level, a particular level of notch signaling, it's specified as a notch cell. And then we specified the adhesivity to be high with the neighboring notch cells. And conversely, if it had lower than a certain level of notch signaling, which would make it a high delta expressing cell, we made that a delta cell, and the delta cell would have particularly low adhesivity with neighboring knot cells. So with those features, we certainly got this behavior. But in the course of developing this program, we got some very nice input from TJ, who told us about another feature of CompuCell, where we use a module called adhesion flex, which allows us to have cells express their adhesivity become a function of some specific adhesion molecule that is expressed by the cells. So one of the things we started out this morning to do was to try to replace this adhesivity that was based on the contact module with one that was based on the adhesion flex module. So I think at this moment, 3 of us were trying to do it independently. I had gotten some, at some level, actually this particular model that I'm running actually has the adhesion flex in it, but I don't think I've implemented it correctly, and it's sort of, the model is running, ignoring whatever I have put inside it. And it's relying still on the contact module, because if I comment out the contact module, the model breaks and it stops being. So I think that though I've put in this other code, somehow it's not actually interfering with the original module, and it's basically running on the basis of what it was doing earlier on. So I will stop talking for myself now, and maybe if Monica or Divyoj want to say something, they should contribute. What would they like, if they want to add something?
Okay, you can't use both the contact and the adhesion flex. I think that, well, I don't know what happens if you do that. In principle, they're doing the same thing, so I'm not sure what it actually will define. One way to check that is in the model editor window.
Yes.
If you go into this, we never discussed this, but if you, and this is something that's potential, we've discussed it with a few people, but it's something that we haven't talked about much. If you go into the model editor window and you click, say, here on plugin.
Yes.
That will open up, it's hard, you have to go through some hierarchies, but let's open up this one, for example.
This one, yeah.
No. And now we scroll down a little bit. And now I can change that value as the simulation is running.
Yes. Oh, I see.
And at least you'll know if the simulation is using that, because you should see a change in the simulation. So if I make that go from 20 to 2 here.
Right. So I have this other plugin in here, but I think it's non-functional. Yeah, it doesn't.
Let's try changing a parameter. Let's see. I don't know what the. Let's try. Let's open up the adhesion flex.
I mean, I think that it's actually the implementation was not completed properly. So for some reason, well, in some sense, luckily for me, the model still works, but it's just ignoring probably what this is doing. Because I don't know that if I comment out the contact thing, then the model gives me all kinds of errors, and the errors are that it points to are the commented out block that is no longer working. So the only reason it's working is that the contact module is in operation, and for whatever reason, the way I have put in the adhesion flex is not working, but it's not interfering with the thing at this stage because it's simply not operational. Okay. So I don't know if Divyoj and Monica, if y'all put it in and what your experience was or how far you got with that. I don't know if they're on. I thought they were, but maybe they're not.
I'll be happy to jump in and work with you on that. But I was just going to say, if you just jump in here and try, let's open one of these values here. Open one of these values.
So like this?
No, here.
Oh, here.
Yeah. And make that number 20.
Okay. Oops.
20.1 because it's supposed to be a float.
Oh, okay.
20. And you have to hit enter. Hit enter first. You have to hit enter, it won't log it.
One sec. What did I
That's
do?
fine. Just make it 20. 20.1 and hit enter. No, you have to click on it. Fine. Hit enter.
Okay.
Okay. And now, if it doesn't change anything, you can be pretty certain that that's not doing anything.
Yeah, I mean, so far it changed it dynamically. While I don't have to stop and start the.
No.
Yeah, so I don't. As I said, I don't think it's actually doing anything, because it seems unchanged for the most part.
I'll jump in and we can see about debugging. Gilberto and Giuliano probably also.
I don't know if you actually hit enter because the text is still selected. So I'm not sure.
But you put 120, not 20.
Yeah.
Well, any value should be all right as long as it's different. But you have to hit enter. Yeah.
There we go.
Okay, yeah. Yeah, that's supposed to be working.
Well, we'll come back to that. Is there anything else from your group that we want to go over quickly?
Not at this stage, unless the others want to say something. And Yi, actually, we lost her yesterday while we were doing it at some point, but I think she's on right now.
I don't. Is Yi there?
Or maybe I have to.
Yes, I'm here.
Hi. So there were some questions about vascular modeling. I don't know if you're willing to help the tumor people a little bit with the vascular model.
Vascular modeling. Yes, yesterday when we talked, I actually thought their intention was to look at the mechanical properties of a cancer cell entering the blood vessel.
No, I think it's more of a classic HUVEC culture with cancer cells cultured around the HUVEC. So it's much closer. It's much closer to the 3D, the self-organization, vasculogenesis, and then the cancer cells are on top of vascular.
Right. Then it's a lot closer to Rowland's work.
Yeah. Yeah. Exactly.
And I'm not sure whether they really need the flow.
To begin with, maybe not, but they'd like to. They have their own flow model. So if we pass them the tubulogenesis, actually, Javier, you could give them your code for segmenting the vasculature. If they to get the vascular tree network out of the CompuCell structure, it'd be possible. So maybe Javier, you could join their group a little bit and talk to them too. Okay. Let's just keep going. I don't want to take the whole day I think it's important that everybody hears what people are doing, but I also don't want to take the whole day since you want to work on your projects too. Tubry modeling, Evan, do you want to give us a quick update?
Sure thing. Okay, let me share my screen here.
And I hope it's helpful to see. And there's so many similarities of issues between the projects. To me, at least, I see a lot of overlap.
There definitely are. I've been noticing it as well. We spent, Dominic and I spent a lot of yesterday trying to get the initial configuration of the 2D sandbox geometry up and going. And so we used some of James Sluka, I hope I'm pronouncing that correctly. We used some of his code from a different project, which creates these circular, configuration kind of around the clock surface using an angle. And we just set up two different radii and created two different circles with two different cell types, one for basal and one for apical. And then if you play, by changing the volume constraint, they fit together quite nicely. So the idea for today, I hope, is to generate and dump a PIF file with this information so that we can just start out with this initial condition rather than the other setup I just had. Creating links that are semi-persistent, I guess, and then potentially adding in a lumen cell type, which would hopefully inhibit it from collapsing on itself as we start changing some of the parameters. So that's where I think I'll be at today.
Okay. I mean, something that'll come up both in this one and the previous one is that if you really want to get something that's more elaborate where the cells are polarized, by default, every part of the surface of the cell is identical. And so if you want to actually have polarization of the cells, then typically what you have to do is create a compartmental cell. And typically we would do that by defining, for example, an apical region of the cell, which would have lower adhesivity than the other regions.
Sure.
So in that case, this apical region here would stick to medium because it doesn't stick to everything else. And that can stabilize your system.
Right.
And also, since also for rosettes, since what you get typically, for example, in rosette formation, is that they're actually contractile, I need a different color. There actually would be contractile links here where you have apical constriction going on at the top surface of your cells here, and then junctional adhesions that are transmitting the forces between them. If you define an apical compartment, then you can define links between the cells and also a contractile force in the apical compartment. And that's a way of getting rosette formation. I don't think Priyam is going to be able to join us today, but she's done quite a bit of work on rosette formation. And it takes a little fine tuning to get the forces to balance each other properly. But the example that Priyam showed in class, I think you have the code from her example. This is maybe a little bit more for the lateral line people, but that code could be used very well for both the lateral line project and for this one. I don't think Julia is on today either, but Julia also published a nice paper using that method. And I'm sure he'd share that code with us. That paper is, let me just grab that reference. That paper is this one here. And so people can take a look at that too. Okay, great. Anything else you want to go over now? It looks like you're getting initial condition that works, and I'll be happy to talk to you.
Yeah, I've got plenty to work on so far, so I think I'm okay.
Okay, so then our last one, which actually probably is rather similar to the one we just heard, was the ovarian follicular dialysis. Romain, do you want to give us an update?
Yes, okay. Yeah, so we work with Joel and Joshua. It was really nice. And okay, I'm trying to share my screen. So yeah, I'm doing a lot of stuff, and obviously it's not working. Anyway, it's okay. This one is more or less working. So I was modifying the code. So we start with defining the geometry of the initial condition with our germ cell in the middle and the somatic cell surrounding it. And we added the divisions capable and the growth of the germ cells. And then we also add the external fields, the diffusion external fields that will feed up nutriments to the somatic cells. So that take up and divide with this. doing a little bit of plot. So we spent quite a bit of time puzzling with the scaling. So we have an ODE model, and so that I'm doing right now. I'm trying to plot the ODE model and figure out whether the scaling are correct. So switching from days to MCS and from micrometers to voxels. So that's where we are. I would say that the first step of the model is done. So we have a more or less fine growth of the somatic cells, the initial steps. And then we have to deal with this next step where the liquid cavity appears. So that could be after we are done with the ODE model, that could be the goal of today, probably. To add a cavity that grows inside this stuff.
That's something. Gilberto, did you join that group at all? Because that's something. Remember your ancient
Yes.
Hydra burst simulator.
No, I haven't been there yet.
Okay, so maybe you could work with them a little bit today and get some help on getting a central fluid-filled cavity.
Yes, okay.
I mean, your simulations predate links, so it's probably easier to do it now than it was in those days, but you have expertise in that problem.
Okay.
So that's great. And so I guess people, I don't want to take too much of your time, but let me just show you. I had really planned, let me see, give me 1 second here. Any general conversation before we want to go back to breakouts. I know some people are new and they're welcome. If people who are new in the group want to join a group or talk about potential additional problems, you're welcome. But I hope that this was productive. Again, I'm glad to see people are making progress. And I just wanted to show 1 or 2 slides here. Because there was a set of questions that came up. And that is here. So there are a couple of things to think about when you're talking about diffusion. And I had this conversation with some people yesterday, so I appreciate your patience if it's a repetition. When you think about diffusion, typically the absolute amount of chemical or concentration of chemical isn't something that's meaningful. We don't really know what those amounts are, and in the simulations, those amounts, absolute amounts, are not terribly meaningful. What does matter is relative amounts. And in particular, there are 3 numbers that are important. And those numbers are diffusion lengths, which is how far does a chemical that's secreted in one place get, typically. Diffusion time, which is if you start out with no chemical and you start putting the chemical into the system, how long does the chemical take to get from where you started to where you wound up? And then equilibration time, which is when you make a change to a source or sink of the chemical, how long does the change take to show up in the system? And of those 3, probably the diffusion length is the most important. And typically in your simulations, if you get the diffusion length and the diffusion time right, then the other things about diffusion don't matter. And so it's important to remember that those are the 2 parameters that are physically meaningful, and that the diffusion constant by itself and the decay constant by itself are not necessarily so meaningful. And so the key thing you want to know is what the diffusion length is in particular. And if we talk about the diffusion length, if we have a diffusion equation where we have diffusion constant D and a decay constant gamma, and that decay constant might represent not just decay of the chemical, but also uptake of the chemical. For example, if the cells are taking oxygen up or glucose up, then the decay constant would be the uptake rate. Then we can derive that the diffusion length is the square root of the diffusion constant divided by the decay constant. And so that means that if I take my simulation and I multiply my diffusion constant by 4 and my decay constant by 4, I don't change the diffusion length. And so as long as the diffusion length is right, I have some freedom to adjust the decay constant and the diffusion constant. So if I multiply them both by the same number, nothing changes. Now, clearly something changes because the diffusion constant is different, the decay constant is different. But the distance that the molecules get from a source doesn't change. And that's actually the most important thing. The diffusion lengths typically are known for molecules, even if the other parameters aren't. The other thing that's going to be important is what the time scale, the diffusion time to get a given distance is L squared divided by D, the distance squared divided by the diffusion constant. And so if I have a molecule that starts here and it goes here, it takes a second to go 1 micron. It will take twice as much, 4 times as much to go 2 microns, and 9 times as much to go 3 microns. And so the time it takes for a signal to get a given distance, and Giuliano talked about this the other day, goes as the square of the distance. And that depends on the diffusion constant, but not on the decay constant. Similarly, the equilibration time, how long the system takes to equilibrate, depends only on the decay constant. The equilibration time is 1 over the decay constant. And so you have 3 independent things. The equilibration time, how long the system takes to reach steady state after a change, is 1 over the decay constant. So diffusion length is the square root of the diffusion constant divided by the decay constant. And the diffusion time is the distance squared divided by the diffusion constant. And so those are the 3 physically meaningful things. And you have to back out D and gamma from those. So I think that's one thing to think about carefully when you set up diffusion equations. If you have a situation in which the diffusion length is too short, and you can see that by saying that the gradient is too steep, you know that you either have to make gamma smaller, the decay constant smaller, diffusion length constant bigger. If the thing is too slow to equilibrate, then you have to increase the decay constant. If you want to keep the diffusion length by the same, then whatever you multiply the decay constant by, you have to multiply the diffusion constant by. And so that's something to think about. The other thing to think about is secretion. Typically, we think about molecules being secreted at a constant rate by cells, and that may be true in some cases. But then the amount that builds up can go to infinity if there's no decay. If I keep churning out pollutants in the world, the amount of pollutant keeps going up. And so in that case, the equilibrium value for your chemical is given by the secretion rate divided by the decay rate. And it'll tend to fluctuate an awful lot. If, on the other hand, you'd specify secretion by specifying the amount of material or concentration of material at the surface of your cell, and that would correspond, for example, to oxygenation in the blood from the bloodstream. Your blood vessel will have an oxygen partial pressure at the surface, which will change a little bit depending on metabolic rates, but is basically fixed. And so if you have secretion not by amount per time, but by fixing the boundary condition, that's much more stable, numerically much more stable, and it gives you much more control over what's happening. And so if you use these ideas of secretion rate, constant time secretion versus constant value secretion, and control of diffusion length, diffusion time, and equilibration time, that gives you a handle on what's happening biologically. And then you take those constants, which you know from the experiment, translate them back into the parameters D and gamma and the secretion rule. And if you start by thinking about what's meaningful in terms of lengths and times in the biological system, it makes it much easier to design the diffusion solvers. You don't have to guess what the diffusion constant and decay constant are. So I wanted to just talk about that a little bit because it's come up a couple of times in the things that we were discussing. Okay, are there any other questions or discussion before we do our breakouts? People who are not speakers will have to remind me what rooms they want to be put into. But anybody else have a suggestion, comment before we do our assignments? No? Well, in that case, I'll see you back in 3 o'clock for a quick check. I'll try to keep it really brief that time. So just a quick check-in to give us a heads up. I'd like everybody to come out of the breakout rooms at 3, do a quick poll of everyone. Then we'll go back into breakout rooms until 5 when we'll do a report. Okay? Looks forward to working with you today. Okay, so Anurag, where do you need to go?
The thymus modeling.
Devoy, where do you need to go? Ariana, where do you need to go?
The cyanobacteria, motility.
Jimmy.
Thymus modeling.
I'm sorry, I should have, you know what? I should have asked people to send me a list of which groups they were in. Joel.
I'll go to Ovarian.
Josh was thymus. Sandeep. Sandeep. Okay. Kai-kun, where do you want to go? Okay, I still have a bunch of unassigned people. AJ, I put you back in. I'm sorry, I clicked the wrong button. I put you back in the lateral line. Kai-kun, I don't have a Monica. Monica?
Lateral line development.
Okay. Okay, Yaling?
I got the vascular tumor one.
Okay. Chang Yu Yuan. Where do you need to go?
To the group of immunity and thymus, please.
Right. Okay. Abby, do you know where some of the people were?
Yeah, Kai Chun is in tissue engineering.
Okay. And then who else? Devoy.
Divyaj is in, he was doing Delta Notch, right? So that makes him in
Caroline.
Yeah.
Okay. And then Zhang Yuan.
Those people look new to me.
AJ, you should have an invite to join the lateral line group. It says you haven't accepted it, and Divya, you also have an invite to it. So you have to look for how to join your breakout session. I can move you out and move you back if that would be helpful. Here. Okay, it's saying, AJ, it's saying it's waiting for you to respond to the invite.
Somehow I am not seeing it anywhere. But it usually pops up in the middle of my screen. Let's see if I can find where it might be. Oh, you know what? Maybe I'll close the chat and it'll open something. Oh, no. Very odd. I'm not sure why I can't see it. Oh, here we go. Got it, got it, got it, got it. See you.
Okay, thank you. Okay, so for our group, who wants to go where? Josh?
I'm working with the Follicular group.
Okay. It might be good for you to walk around a little bit because I think a lot of people could benefit from your insights, but I'll put you there. So.
Okay, that's fine.
Okay. Jim S., where do you want to go?
I don't have any place in particular. It'd be best if somebody would email me when they actually have something specific.
I think that the tube remodeling is only one person. If you could help him a little bit, that would be great.
Okay.
Javier, do you want to talk to the vascular people about maybe the idea of doing some, explain to them a little bit about how you did the flow models work? I don't know how sophisticated they are at this point, but they probably would like that if you would. Javier, you there?
Yeah, okay, that's fine.
Okay, thank you. Giuliano?
I was with Timus.
I can put you back there and maybe again you could walk around a little bit.
Yeah, I was already thinking about doing more of that today.
I'm sorry, I wish there was some way you could move yourselves, but I don't think there is. Andy, welcome back. Do you have anybody you want to help out? You want to work more with?
The cyanobacteria.
Okay, great.
Oh, and I think, hold on. I think if you're co-host, you can put yourself into a room. I think, I'm not sure though.
Yeah, if you're co-host, you can put yourself in the room, but you can't assign anybody else. So somebody's and you can only go into one room. I think you can only go into your assigned room. I don't think you, anyway.
So, but if you're, what if everybody was co-host? Could they move to any room they wanted to?
I don't know. Let me make you co-host. Are you co-host at the moment?
I don't think so.
I'll put you in tissue engineering for the moment. Again, if you can sort of wander around a little bit, that would be good. But let me make sure before co-host. Gilberto, do you have anywhere place you want to go?
Well, I think I should go to the vascular tumor to start today, because this is the place I went yesterday.
I'm sure people would benefit. I think, for example, the ovarian people would benefit from your work on that, the old work on hydra bursting.
Okay. Mm-hmm.
So,
which group is that?
That's the ovarian follicular genesis. That's the bottom one.
Hmm. Okay.
But I can put it. So Javier is talking to the vascular tumor people at the moment.
Then I can move a little bit to the tissue engineering about the pillars and the cancer one.
Okay, so which one do you want to start with?
Wherever you need.
Well,
but
they're all.
The first one, that one you talked about, the hydra stuff.
Okay, Andy, where did you want to go?
The cyanobacteria.
I mean, there's several groups that could use what you're doing, so it's, you should.
Okay. Sure.
Okay, all right, Tarun, we can talk a bit. What's up?
Okay. Yeah. Do you want to share my screen?
Okay.
Yeah. So here is that model I was running, and I've got 10 sets of parameters to change, but I haven't included them. So what I am looking for, so to put them in a loop, like if I can iterate lots of sets of parameters for in that model.
So you want to change the parameters within the model?
Yes, if I can. I'm not sure how to do that.
Okay, so I mean in principle, you could restart the simulation in the you. I wonder what's the best way to explain that to you. So it's possible to run CompuCell from a command line.
Okay.
And when you run from a command line, you can pass parameter values. Now the way you do that, I think if there's how's the easiest way to describe that. So there are a couple of ways you could do it. The problem, we have parameter scan functionality in CompuCell.
Yes, I've seen.
But it doesn't give you the Latin square parameter values that you want.
But I have generated them in somewhere else. So how can I input that set of parameters?
Sure, you could certainly open if you put them in a file, you can open the file and read it.
Yeah, that's what I am like trying to do.
Okay, so what we'd have to do is so there are a couple of things. One thing I mean, the problem, my only problem is I didn't write this particular code, and TJ wrote it in a way that I find a little bit, let me stop.